Hello, students, and welcome to today's lecture where we are going to be covering the topic of chemical equilibrium. And today's first video is supposed to be essentially about the core concepts of chemical equilibrium and what are really the characteristics of what it is and what's going on. So, right here, what we have is a typical example, and this is one that we've already done a lab with before. Okay, and this is something that happens with copper sulfate. Now, copper sulfate can exist in two different states. Okay, it can exist in a hyperhydrated state where it has a whole bunch of waters attached to it, or it can exist in an anhydrous state. And an anhydrous state essentially means that it has no water in it whatsoever. Okay, so in the first case, what I want you to take a look at is you should see that there's a very, very bright blue one in the corner. And that very bright blue one that's in the corner is the copper sulfate that has the 5 waters already attached to it and inside of it. And as we heat that up and dehydrate it and cause that water to leave, what will happen is that it'll go from this bright blue to this not so pretty grayish blue right here. Okay, and that's one reaction that could happen. At the same time, though, what you'll see is that it also goes from the grayish blue to the bright blue. So it's also absorbing that moisture from the air. Okay, and so what happens is that when we are messing with copper sulfate pentahydride or copper sulfate anhydride, what we're actually doing is we're causing both reactions, or we're messing with both reactions that are happening at the same time. Okay, and in general, what'll happen is that we'll get to a point where these reactions end up being at equilibrium. Okay, so the key thing that I want you to realize first here is that equilibrium is actually two reactions that are happening at the same time. Okay, here is another one. Okay, this is a reaction of N2O4, and it's being converted from N2O4 to NO2. Okay, so what happens is that gradually the N2O4 transforms into NO2, and as that happens, it goes from a clear solution to a brown solution. Okay, and this is just a secondary example here. And in equilibrium, what we're going to find is that we're going to have a case where we have both reactions occurring, and we'll get to a point that both reactions are going to occur at the exact same rate. And when they start to occur at the exact same rate, will be known to have what's called equilibrium. Now here, this is a graphical representation of equilibrium, and what I want you to notice is that the N2O4, which is this clear liquid that we started here, initially has a high concentration, and that the N2O2, the NO2, has a low concentration. And that gradually as time goes forward, what happens is that the concentration of the low one gets higher, the concentration of the higher one gets lower, and we end up reaching a rate for these reactions where they end up being equal. Okay? And that point at which they end up being equal and the rate of reaction for both of these reactions is equal is what we know as equilibrium. Okay, so that means that just as many particles of N2O4 are breaking apart to make NO2, and as many particles of NO2 are hitting each other with enough force to make N2O4. Okay, so both these reactions are happening at the same time, and we're not actually getting any noticeable change because both reactions are happening at the exact same rate. And the rate and that point where that rate occurs is our equilibrium point. Okay? And here we go. This is an example that shows the exact concentration. So even if we start with a whole bunch of N2O2, what you'll notice is that we're going to decrease the concentration of N2O2, okay? And this is essentially us saying that we have a starting point of just N2O2. As the reaction goes forward, the concentration of N2O2 will decrease until equilibrium is reached, and then our concentration is going to stay the same, okay? And the only real difference here is that this one here is the rate of reaction, and I want you to notice that the rate of reaction both are equal. Here, this is our concentration, and our concentration of NO2 ends up being higher, which should make sense to us because we have 2 NO2s for every N2O4 that we make, okay? And so this is what's going on at equilibrium, that eventually we'll reach a point where one thing is going to, where both of our products and our reactants end up having the same concentration no matter how much time has been evolved in this particular reaction, okay? So, in this case, rates will become equal and concentrations will become equal, okay? One thing I also want you to note is that this is going to be the symbol that we will use to indicate that we have a reversible or equilibrium type reaction going on here. Okay. And there are some characteristics that I want to make sure that you guys know and are able to define. And think of this as kind of like some of those, first initial gimme questions that'll be on like any sort of test on this. And the first one is that all of these are dynamic. All of these equations and reactions are dynamic, okay? And what we mean by dynamic equilibrium means that the molecules or ions are continuously reacting. They haven't stopped reacting. They're still reacting. They still have this constant rate of reaction that's going on. It's just that the particles that are being depleted are being replaced at the same rate that they're being depleted, all right? So that's the first thing, that they're dynamic, okay? Second, during equilibrium, the forward and backwards reaction are occurring at the same rate, okay? The third characteristic is that the concentration of reactants and products are going to remain constant. So once equilibrium has been reached, that means that it's going to stay a constant, will maintain a constant amount of both the reactants and the products. And the fourth thing is that it requires a closed system. And this is really important for equilibrium because a closed system is going to be one where we're not allowing any of the reactants or products to escape from the reaction. In an open system, the matter can be lost to the surroundings, and that'll cause us a whole bunch of different issues, okay? And to further go into this, we have an example. One is going to be like a chemical example. And in this case, so for instance, if we go ahead and heat up calcium carbonate, what will happen is that it turns into calcium oxide and CO2. And in a closed system, we would have an equilibrium where the carbon dioxide would eventually react with the calcium oxide. And we would go back and forth, okay? And we would end up reaching an equilibrium in that container. Whereas if we had an open system, which this one is, okay, the bottom one is an open system, what you'll notice is that the carbon dioxide will just escape. And if the carbon dioxide escapes, that means that the backwards reaction will not have any products that it can use. Okay. And the following here is just like another example of the three types of systems. The first is an isolated system. Okay, this would be something where it's completely isolated from the outside. We don't have any heat or energy being transferred in. It's perfectly insulated, and matter can't get in, energy can't get in. perfectly isolated system. A closed system is going to be one where energy can get in, but matter cannot get in. And the last thing is an open system where both energy can get in and out as well as matter. Okay? And that's going to be it for the more basic explanation about what equilibrium is. And we're going to go ahead and close us off here. Okay? I even have this stop for lecture 1. All right. You should be able to work on your beginning worksheet for this one. Okay? And I would like for you to be reminded, with the first video of the quarter, to please remember, stay lazy.